Let's talk about vector line integrals and vector line fluxes. And let's stick to R2 for now so that we're in the plane. Suppose you have this curve C in the plane. And you also have a vector field defined in that plane. Here I'm just drawing the vector field just at one point along this curve C. But we could imagine the vector field actually taking on more values depending on what point you're looking at. Say you could point here at that point and here at that point here, and even along this curve, maybe the vector field would point this way at that particular point. Of course, a vector field is defined for the different points in the domain. But we're focusing here now on just the curve C. And how do we take a line integral of this vector field along the curve C? Well, we'll take the vector field at a particular point, is what we see here, and we could dot it with this dr. Now dr points along the tangential direction. That vector there will point tangent to the curve. So we dot the vector field at that point with the tangent vector at that point and multiply it by the length, small length, ds there. Okay, and here you see the vector field, you see the formula for doing it. Okay, you're dotting with the tangential vector. Well, in R2, and then specifically in R2, you could look at a direction perpendicular to this tangent vector and call it the normal vector. Okay, this is this dn that is defined as n hat ds. So here we have the normal direction, and we could multiply by the small length ds. And now this there are two normal directions, so you have to specify which one. So you could either have pointed up as we drew it here, or pointed down, and the problem should specify which normal direction you're looking at. In R3, we're going to have to modify the meaning of flux, as there's actually, if you could imagine this normal vector rotating all around the curve C. So it's we're going to have to modify what the meaning of flux is in R3, and we'll actually look at fluxes through surfaces, not lines. Okay, here we're just looking at a flux through a line, and we're sticking to R2. How do we get that normal vector? Well, we could take the tangent vector, okay, and borrow k hat. K hat points in the positive z direction. And we could do t cross k hat, okay? And your thumb should point in the direction of n hat. That's one way to get the one of the normal vectors to a curve. And if you do that, you'll get this expression at the end once you get your tangent vector, okay? So you could do that and you'll get this expression, and you could simplify. You can plug the vector field, which is this, and you could take that expression and plug it in here, and you end up with that formula there. Once you also plug ds into here, you end up with this formula. And a quick remark here. Some of you may have noticed that I was talking about the plane R2, but somehow I brought the z-axis into it. Here we're just borrowing the z-axis, okay? This curve will live in R2, but we're going to borrow the z-axis because it makes computing the normal vector easier once you have that tangent vector. Okay, so it's just borrowing, but we don't really use it explicitly anywhere in our formula for the vector line flux. You'll also see some alternative notation for vector line integrals and vector line fluxes. So if I write out f as fgh and dr as this vector here, okay, you could dot these two and you'll get this expression. Now you could see this for a vector line integral. And many students get confused because they remember that dx from Calc 2 and they think it's the same thing over here. Well, here it's a more general dx, and the formula for it will be x prime dt, where x prime is the x component of your parameterization. If you'll recall, the parameterization looks like this. Or to be a little more explicit, we'll write it as x of t, y of t. Okay? And so you could take the derivative of this expression in your parameterization, multiply it by dt, and likewise you could do the same thing for dy. You take y prime, you take the y component of the parameterization, take its derivative, multiply by dt, and you'll be left here with an expression that has dt at the end of each of these, okay? And that's what you're actually integrating over dt. So it's not the same thing that you would do in Calc 2, so be careful when using that. Also, I'll make a quick remark here. This is in R3. Okay, vector line integrals, to generalize from R2 to R3 is very easy. You just have this extra term there. But again, for vector line fluxes, they're only defined in R2. Once we get to R3, there is a notion of flux, but we'll have to use surfaces rather than lines there. So that's the remark I wanted to make about that. And here you could see this general picture of vector line integrals and vector line fluxes. For vector line integral, we would keep taking f dot t hat and multiplying it by the little infinitesimal ds as we move along this curve. Okay? For the vector line flux, it's not t hat but normal to it. So we would dot with the brown vector and move along this curve. And the idea of borrowing the k hat, this is why we do it, okay? But as you could see, the curve is actually just in the xy plane. We're just sort of borrowing k hat only to get a formula. Once we get the formula, we could ignore the k hat. And here we could show both tangent and normal vectors, which are orthogonal to each other. And you could see that you could project f onto either the normal vector, okay, that's how you would view f projected onto the normal vector, or the tangent vector, depending on whether you're doing a vector line integral or vector line flux. And what is the integral? Well, after you dot f with either n or t, and you multiply by the infinitesimal ds, well, you got to add up all these pieces, right? If you're doing a work integral in physics, you're dotting with t, and you add up all of the small works that occur as you're moving around the curve c. If you're calculating the flux, you'll add up all of the f dot n times the little distances as you're moving along the curve c. So let's do a quick example here. Let C be the unit circle with counterclockwise orientation. Okay, so t hat points in the counterclockwise direction. Compute the vector line integral, sometimes called the circulation, and vector line flux of the vector field. So when you have a closed curve, okay, C, and say you're going counterclockwise there, sometimes you'll see the integral notation like that whenever you're using a closed curve. You just get an extra circle in the integral sign. And so that's called the circulation when it's closed, and the flux also along this closed curve. So we're going to compute both of those for both vector fields that you see here. Fxy, which is radial. If you want to see how it looks, it's always pointing out. Okay, anywhere you move along, it's also getting longer, the vectors as you move out. And gxy, and here they're also getting longer, but you could see that they're moving in this sort of tangential way. Okay. So let's compute the vector line integral and vector line flux for each of these, fxy. Hopefully your intuition is telling you that the vector line flux should be positive and the vector line integral should be 0 for this radial field because it's pointing outwards. Okay, so when you dot it with the tangent vector, and don't forget the tangent vector is always pointing tangentially, okay, to this circle. So you're always getting 90 degrees between your vector field and the tangent vector, okay? You're always getting 90 degrees between the vector field and the tangent vector. So you expect that it is 0, and indeed you could do these formal steps of parameterizing the curve. And here's our parameterization. We take the derivative and we use the formula f of r of t dot with r prime. Okay, plug the parameterization into your vector field and do the math and you'll get 0. Now what about the line flux? Okay, you got to be careful. The formula for line flux looks like this. Okay, and when we plug in our parameterization, we still get x of t and y of t, because that's what f is, x and y there, pretty simple. And we dot it with this vector here, and we end up getting 2 pi as we should have, right? And the reason is that the normal vector points out this way, okay? So you're dotting with a normal vector here that all the way through, and they point along each other. So you're adding up all of these dot products as you move along, and you end up with 2 pi. Okay. Now, gxy should have the opposite relation in the sense that the circulation should be positive, and it is, and we could do the same formal steps. And it's clear why that's the case. Again, here's gxy, and here's tangent vectors. They point along with the vector field. On the other hand, the normal vectors point out, and there's 90 degrees between them, and the dot product between them then will be 0, because cosine of 90 is 0. So we get 2 pi for the circulation, as we expect, and doing this formal integral, using the formula, we get 0, okay? And again, here's the formula that we used. Once you have your parameterization, you just plug it into your vector field and you compute. And we end up with these relations. So hopefully now your intuition is built around what the line integral means and the line flux means.